Smart Figure 18.41 Orbital Variations. Periodic variations in Earth's orbit are linked to alternating glacial and interglacial conditions during the Ice Age. Tutorial. Orbital forcing of ice ages. Using these factors, Milankovitch calculated variations in the receipt of solar energy and the corresponding surface temperature of Earth back into time, in an attempt to correlate these changes with the climate fluctuations of the Quaternary. In explaining climate changes that result from these three variables, note that they cause little or no variation in the total solar energy reaching the ground. Instead, their impact is felt because they change the degree of contrast between the seasons. Somewhat milder winters in the middle to high latitudes mean greater snowfall totals, whereas cooler summers bring a reduction in snow melt. Among the studies that have added credibility to the astronomical hypothesis of Milankovitch is one in which deep-sea sediments containing certain climatically sensitive microorganisms were analyzed to establish a chronology of temperature changes going back nearly 500,000 years. This time scale of climate change was then compared to astronomical calculations of eccentricity, obliquity, and precession to determine whether a correlation existed. Although the study was very involved and mathematically complex, the conclusions were straightforward. The researchers found that major variations in climate over the past several 100,000 years were closely associated with changes in the geometry of Earth's orbit, that is, cycles of climate change were shown to correspond closely with the periods of obliquity, precession, and orbital eccentricity. More specifically, the authors stated, it is concluded that changes in the Earth's orbital geometry are the fundamental cause of the succession of quaternary ice ages. Asterisk. To briefly summarize the ideas just described, plate tectonics theory provides an explanation for the widely spaced and non-periodic onset of glacial conditions at various times in the geologic past, whereas the theory proposed by Milankovitch and supported by the work of J.D. Hayes and his colleagues furnishes an explanation for the alternating glacial and interglacial episodes of the Quaternary. Other factors. Variations in Earth's orbit correlate closely with the timing of glacial, interglacial cycles. However, the variations in solar energy reaching Earth's surface caused by these orbital changes do not adequately explain the magnitude of the temperature changes that occurred during the most recent ice age. Other factors must also have contributed. One factor involves variations in the composition of the atmosphere. Other influences are related to changes in the reflectivity of Earth's surface and in ocean circulation. Let's take a brief look at these factors. Chemical analyses of air bubbles trapped in glacial ice at the time of ice formation indicate that the Ice Age atmosphere contained less carbon dioxide and methane than the post-Ice Age atmosphere, figure 18.42. Carbon dioxide and methane are important greenhouse gases, which means they trap radiation emitted by Earth and contribute to atmospheric heating. When the amount of carbon dioxide and methane in the atmosphere increases, global temperatures rise, and when there is a reduction in these gases, as occurred during the Ice Age, temperatures fall. Therefore, reductions in the concentrations of greenhouse gases help explain the magnitude of the temperature drop that occurred during glacial times. Although scientists know that concentrations of carbon dioxide and methane dropped, they do not know what caused the drop. As often occurs in science, observations gathered during one investigation yield information and raise questions that require further analysis and explanation. Figure 18.42 ice cores contain clues to shifts in climate. This scientist is slicing an ice core from Antarctica for analysis. He is wearing protective clothing and a mask to minimize contamination of the sample. Chemical analyses of ice cores can provide important data about past climates. Photo by British Antarctic Survey/Science source. Obviously, whenever Earth enters an ice age, extensive areas of land that were once ice-free are covered with ice and snow. In addition, a colder climate causes the area covered by sea ice, frozen surface seawater, to expand. Ice and snow reflect a large portion of incoming solar energy back to space. Thus, energy that would have warmed Earth's surface and the air above is lost, and global cooling is reinforced. Yet another factor that influences climate during glacial times relates to ocean currents. Research has shown that ocean circulation changes during ice ages. For example, studies suggest that the warm current that transports large amounts of heat from the tropics toward higher latitudes in the North Atlantic was significantly weaker during the Ice Age. This would lead to a colder climate in Europe, amplifying the cooling attributable to orbital variations. In conclusion, we emphasize that the ideas just discussed do not represent the only possible explanations for ice ages. Although interesting and attractive, these proposals are certainly not without critics, nor are they the only possibilities currently under study. Other factors may be, and probably are, involved. 18.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the basic theory behind the orbital forcing of ice ages. In other words, how small changes in the Earth's orbit around the Sun can end up resulting in ice ages either turning on or turning off. If you were to go back in time about 18,000 years, you'd find a very different looking Earth. In the northern hemisphere, huge ice sheets would cover much of the continental landmass. In general, it was a much colder time. One of the leading ideas for what turns ice ages on and off are so-called orbital effects. And these basically are three major ways in which the Earth's position relative to the Sun changes over time. The first orbital effect is shown here. The Earth's orbit around the Sun is sometimes a more perfect circle and sometimes a less perfect circle. In other words, it varies from pretty much a perfect circle to a more elliptical shape. And this variation takes place over a cycle that lasts about 100,000 years. Obviously, when the Earth is closer to the Sun, it's going to be getting more energy from the Sun. And when the Earth is further away from the Sun, it'll be getting less energy. So that orbit, whether it's circular or elliptical, describes a plane in space. And the Earth is sort of encased in that plane. But the Earth's axis of rotation is not perpendicular to that plane. Instead, it varies between about 22 degrees away from perpendicular and 24.5 degrees away from perpendicular. Today it's around 23.5. But basically what this means is when you've got a greater amount of tilt away from perpendicular, that means you're going to have greater amounts of seasonality. In other words, winter will be colder and summer will be warmer. That varies on a cycle of about 41,000 years. This is called obliquity. Finally, we have precession, which is also known as wobble. So the Earth's axis of rotation, that line in space, actually ends up pointing to different directions over time. So right now, of course, the axis of rotation is basically lined up with the North Star, or Polaris. But over time, over about 26,000 years, it'll vary and it'll point at a different section of the night sky, like the star Vega. This is kind of like a top that is spinning, and as that top slows down, it begins to wobble. So it's still spinning around its axis, but the axis itself ends up inscribing a cone in space. So when you look at the eccentricity, which has that 100,000-year cycle, and you pair it up with the obliquity, which has the 41,000-year cycle, and then you look at the precession, which is on the order of 26,000 years, you can add those different curves together. Each of those cycles ends up basically imparting more or less of the Sun's energy to a critical latitude, which is thought to be around 65 degrees north, up there in the northern hemisphere where these ice sheets were forming. Well, when you pair those all together, you end up getting a final curve that looks something like this, roughly. So in other words, this purple line at the bottom is the other three curves added together. And the low spots are correlated with evidence from deep sea sediment cores that indicate the Earth was in a cold climate. In other words, that an ice age was on. And the peaks of those curves indicate times when it was warmer and the ice caps were melting back and the Earth was entering an interglacial period. And that, again, matches up with the evidence from deep sea sediment cores. So, bottom line, slight variations in the Earth's orbit around the Sun end up giving us greater or lesser amounts of heat energy, which basically turns on or turns off ice ages. Thanks very much for your attention. This has been another Smart Figure.